Welcome back, focus learners. Today we're taking a journey, specifically the journey of a tensor. We hear all the time about the magic of artificial intelligence, but today we're demystifying that black box entirely. We are looking directly into the engine that powers it all, matrix multiplication. By the end of this explainer, you're going to see exactly how data moves, transforms, and ultimately learns. Okay, let's dive into this. We'll start with the engine of AI, then visualize the shape collapse principle. We'll translate code to math, fix those annoying shape mismatch errors, go deep inside the GPU hardware, and finally, look at pushing the limits.
Section 1. The engine of AI.
So why does matrix multiplication matter so much? Why is it the absolute, undisputed bottleneck of modern machine learning? Well, I absolutely love this quote from our source material. If the scalar is the atom of machine learning and the vector is the molecule, then matrix multiplication is the chemical reaction. It's not just an abstract math operation, right? It's literally the fundamental computational act that makes deep learning possible. When you see a massive model like GPT-4 or Stable Diffusion generating those mind-blowing results, just remember that over 90% of the floating point operations happening during their training are happening right here inside matrix multiplications. It solves two massive problems at once: composing transformations and processing huge batches of data simultaneously.
To really ground this, think of matrix multiplication as the ultimate matchmaker. Imagine a factory. Matrix A represents our customers as rows and the raw materials they ordered as columns. Matrix B represents our factory's products as columns and the raw materials required to build them as rows. To figure out our final output, which is matrix C, we need to match them on their shared trait, the raw materials. We take a customer's raw materials request and we calculate a dot product against a product's recipe. This dot product just measures the compatibility between the input features and the output features. In an AI neural network, matrix A is your batch of input data, matrix B is your learned weights, and matrix C is your model's output prediction. It's really just an incredibly fast, organized way of asking, hey, how well does this data match this learned pattern?
Section 2. The shape collapse principle. Now let's move into the visual geometry of how these matrices actually combine, which is absolutely crucial if you're an engineer building these systems. We have matrix A, a 2x3 matrix, and matrix B, a 3x2 matrix. Notice that shared inner dimension, the 3? I want you to physically visualize those two inner 3s colliding together. As the dot product calculates, those 3s completely annihilate each other. They're consumed by the math and just vanish entirely, leaving behind only the outer numbers. So a 2x3 multiplying a 3x2 collides, collapses, and leaves us with a perfectly formed 2x2 output matrix.
So, the crucial point is what we call the golden rule of shapes. The inner dimensions, represented by K here, must always perfectly match. They are consumed by the operation and they vanish. Meanwhile, the outer dimensions, M and N, survive to dictate the exact shape of your final output. Seriously, memorize this rule and half of your programming headaches in AI will disappear overnight.
Section 3. Translating code to math. Speaking of programming, let's look at how this geometric theory translates into functional software. The high-level code you'd write in PyTorch is super simple, torch.matb. But look at the low-level logic execution. See how that specific highlighted row in matrix A forms a brilliant visual arc, reaching over and diving down into the corresponding column in matrix B? That arc is the dot product. It's calculating the sum of the element-wise multiplications and planting the result exactly at the intersection point in the output matrix. That single API call triggers thousands or even millions of these beautiful arcing dot products.
Under the hood, modern frameworks give us brilliant shorthand for this. In Python, the @ symbol is explicitly reserved for matrix multiplication. The .t swaps our rows and columns, giving us a transpose. When you call a standard linear layer in a neural network, the framework is really just doing x at w.t plus b in the background. And the best part? It seamlessly handles batch dimensions. If you have a massive 4-dimensional tensor of data, PyTorch knows to just ignore the batch dimensions at the front and only perform that arcing matrix multiplication on the last 2 dimensions.
Section 4. Fixing shape mismatch errors. Of course, the code doesn't always run perfectly the first time. Let's tackle the single most notorious pothole engineers hit when building AI models. Now, what's really interesting here is that giant red X. This is the dreaded runtime error, shapes cannot be multiplied. We're trying to multiply a 2x3 matrix with a 2x4 matrix. Remember our golden rule? The inner dimensions here are 3 and 2. They do not match.
The shapes cannot collide and annihilate. It's a fundamental structural failure, and the framework violently throws an error.
But the fix is actually structurally elegant. Step 1, we identify the offending inner dimension. Step 2, we apply a transpose operation, that .t we saw earlier, to our second matrix. This flips its rows and columns, turning it from a 2x4 into a 4x2. Step 3, look at the inner dimensions now. By transposing the weights, we flip it to features by output. Suddenly, those inner feature dimensions match perfectly. They collapse, and your data flows freely again. There are a few other silent killers to watch out for, too. Forgetting your batch dimension will cause massive broadcasting headaches. Accidentally typing an asterisk instead of the @ symbol. Catastrophic. It performs element-wise multiplication instead of a true dot product, meaning your math is entirely wrong, but the code won't even throw an error. And finally, out-of-memory errors, especially when computing attention scores on long sequences, which simply blow up your hardware limits.
Section 5. Inside the GPU hardware.
Let's move on and see how this builds from a software perspective to a hardware reality. Why do we need multi-$1,000 GPUs just to do some multiplication and addition? Well, if you wrote a naive script with 3 nested loops to multiply these matrices, it would be agonizingly slow. Just a tiny batch of 32 inputs through a standard network layer results in over 4.19 million floating-point operations. A standard CPU loop simply cannot handle this. Instead, GPUs utilize an architecture strategy known as GMM, or General Matrix-Matrix Multiply. And here is the magic of modern GPUs. Notice how the massive matrix doesn't get processed all at once. It breaks down into neat, tiny 16 by 16 blocks called tiles. These tiles are loaded into ultra-fast SRAM memory. Then, watch them fly into the glowing geometric center, the tensor core. This specialized piece of hardware performs that entire 16 by 16 matrix multiplication in a single, blazing fast clock cycle, pops out the result, and finally writes it to the slower main memory. This perfectly demystifies why bigger is better for GPU batch sizes. The bottleneck is almost always the overhead of moving the data around, not the raw computational speed of that glowing tensor core. Because of this, engineers are constantly balancing whether an operation is compute-bound, meaning it's waiting on the tensor core, or memory-bound, meaning it's waiting on data to load from the chips. To speed things up, we use mixed precision. PyTorch uses torch.autocast to store the massive matrices in smaller 16-bit formats to save memory bandwidth, but smartly calculates the actual multiplication inside the tensor core at 32 bits so the math doesn't overflow. It's a brilliant hardware-software handshake.
Section 6. Pushing the limits. So we understand the math, the code, the errors, and the silicon. To conclude, how are researchers pushing past the current limits of these GPUs? And this brilliantly illustrates the core problem of modern AI scale. 268 megabytes. That doesn't sound like much, right? But that is the memory footprint required for just a single attention head in a single layer for a single batch item when processing a text sequence of 8,192 tokens. Because attention mechanisms require multiplying sequence length by sequence length, which is a quadratic complexity, the memory requirements explode instantly. You multiply that 268 megabytes across dozens of heads and layers, and suddenly the most powerful GPUs on Earth are completely out of memory.
To survive this, researchers have actually rewritten the algorithms to leverage the hardware better. Flash attention is a massive breakthrough that calculates the matrix multiplication in those tiny SRAM tiles we saw earlier, entirely bypassing the need to write that massive quadratic matrix to slow memory. LoRa exploits the associative property of matrices to fine-tune massive models using just a fraction of the memory. And M2 call takes image convolutions, which are basically sliding windows, and literally stretches them out into giant rows so they can be processed by the tensor core as standard matrix multiplications. It's all about feeding the matrix multiplication engine efficiently. Which brings us to our final, provocative question. Matrix multiplication built the AI revolution, but it's heavy, it's hot, and it is incredibly power-hungry. The hottest new research direction is exploring MatMul free networks. Can we use extreme quantization, shrinking weights down to just -1, 0, and 1, and replace these heavy multiplications with simple addition? Could the future of AI run entirely without the very engine that got us here? It's a fascinating frontier. Keep your eyes on the research, keep visualizing those collapsing shapes, and stay curious. See you next time on The Explainer.